Hello, it's finally time to speak about the very famous Ohm's law. Just before that, I'd like to put things into context. We had seen in video number 1 the three first points around this circuit, the basic components, closing the circuit, and then how to represent it with formal diagrams. In video number 2, we tackled the analogy between electricity and water, and we focused very much on this same diagram here, in which I would like to say it can introduce us smoothly to Ohm's law. That is because the higher the pressure that can be produced by this pump, or the higher the tank of water that can be providing the pipes, the more we would expect the current of the water to be there. For constant pipe widths, the higher or the stronger the pump, the more water will be flowing per second, the quicker the water will be going. The same applies to electricity. The higher the voltage for constant resistance means if we don't have more and more resistances, the higher the voltage, the more the current, the more amperes, which are number of electrical charges, coulombs, per second flowing through this wire. Now there is a different parameter to consider here, which is for the water system, diameter of the water pipes, and for electricity it would be the resistance. You can see here that if we have larger pipes, we would expect for the same voltage, if the pipes become larger, we would expect that the current can go higher. For resistance, it goes the other way, because resistance is a word having the negative meaning of width or large pipes. So that's why we should say the less the resistance for same voltages, we would expect the higher the current. Let's see this formally in what we call now Ohm's law. Here, we can state the law in different ways. We can say that voltage is equal to the current multiplied by resistances. Please bear attention that most of the time resistance will be constant, or considered at least constant, and for that we can say that there is a direct proportion between voltage and current. This means that the higher the current, the higher the voltage, and vice versa. The higher the voltage, the higher the current, given that resistance is constant. We express such simple relationships with a triangle, where we say the product V is equal to current multiplied by resistance I by R. We put them in the base divided by 2, such that if we want to get one of any one of these three equations quickly, we just cover the left hand side and we get the equation of the right hand side in the following way. If we cover V, because we want to calculate V, only we will have I and R to each other, so we'll say it's equal, V is equal to I multiplied by R. Similarly, if we want to compute I, the traditional way is to say I should be divided here by R, and similarly the equation will be maintained if we divide by R, so that we get I isolated, and that will make it equal to V by R. Putting it in this triangle makes it sometimes easier. We can cover I, and then we can see that V is over R, so I is equal to V over R. It's only a way of simplifying, finding things, or making easier and faster for people who are new to these equations. Finally, if we want to compute the resistance R, it's the constant ratio between V and I, so it's equal to the voltage divided by the current, which we can see here in this diagram as the slope of this line. We can see in the diagram first that there is a direct proportion between current and voltage. The more the current, the more the voltage, given that the resistance is constant. And you can say it the other way also. If the voltage is higher, it indicates that the current is higher. The line doesn't have to be a 45 degree or so. It can be any of any slope depending on the resistance. So for example, for this line you can say that for lower current we had higher voltage, or higher voltage was needed for lower current, so it's a higher resistance, and that can be seen as the slope is higher than the other slope here. This is a very nice simulator that we'll be using together. It has batteries as power supplies. You can put one or more. Let's start with simple. It has the light bulb, and you can add extra resistances if you wish. You can add a switch. Let's make it simple. Let's wire by dragging a wire till it connects to one side of the battery. You can see that the battery has two kinds of representations. We'll stick to this nice representation for now. Take another wire. I could have put a switch, but I'll just try to connect it to the other side of the bulb with a wire. And to illustrate Ohm's law very clearly, we will try to put a resistor here and change its value. For now we can see the level of illumination. We can measure the voltage, four and a half volts are over this resistor. We can also measure the current, which is 0.45 amperes. What happens if we try to increase the resistance? Would the current go up or down? And consequently, what do you expect the illumination of the lamp will do? Just compare it to the analogy of water. If we increase resistance, it's like putting more and more obstacles into the water pipes. You can see that the current will be slower, it will be less amperes here, and the illumination has become less. However, if we move it now to the other side, making the resistance less than what it was, or even zero, we find that the illumination representing the current has become more. The current itself has become more. I hope you can enjoy having many experiments using more tools like switches, like the coins, like fuses and paper clips, dollar bills, to see how much resistance all of these have. Let's go now to the exercises. This was just a brief introduction to this. Thank you very much.